This is Mr. Haytack from Arapahoe High School, and this is the AP Chemistry screencast for Chapter 1 material and the summer assignment. I used pages 1 to 16 in my comp book for these notes. Assignment that you should be completing before returning in August to school. At the end of Chapter 1, here's the kinds of things you should know. You should definitely know the difference in the definitions between endo and exothermic, kinetic and potential energy, mass and weight, chemical and physical properties and their changes. You should know the law of conservation of matter and of energy. You should be able to identify the characteristics of states of matter such as solids, liquids, and gases. Those are the main three. There are a couple others, and we'll talk about those here in a few minutes. You should be able to identify mixtures as substances, as elements, and compounds, and mixtures, and know the differences and how you can separate them. You should know the metric system units and prefixes. That's very important to your success in chemistry. You should be able to identify the number of sig figs in a measurement, and then you should be able to complete calculations using correct significant figures and the units for the answer. You should be able to complete conversions of temperature, energy, and other measurements such as are found in the metric system by the time you're done with Chapter 1. This should all be basic review from first year chemistry, so we should be okay with it. There's nothing really too difficult in here that I could find, so again, it's a whole bunch of definitions. You guys in this podcast or screencast, you're going to see a whole bunch of different images. All of the images are credited to Wikipedia. They're part of the open source files, so I've just gone ahead and put them in here. Here's some of the key terms as we go through and do this. Matter, which is anything that has mass and takes up space. So then you get to where you need to know a little bit about mass. That's one of the standard measurements in chemistry. Mass is a measure of the quantity of matter. It's represented here in this image based on what a kilogram looks like at the Standards Institute. In terms of energy, there's both kinetic energy and potential energy. Kinetic energy is defined as the energy to do work. It's easily transferred. It's motion. It's work done directly by something, and it's typically expressed as 1/2 mass times velocity squared. Potential energy, on the other hand, this is energy due to position, composition, or condition, and it's commonly referred to as stored energy. So in the image of the basketball bouncing, kinetic energy is anywhere the ball is in motion, and potential energy is where its motion is stopped. So at the top of each curve, where the ball has started to turn downward, it now has the least amount of kinetic energy but the highest amount of potential energy. At the bottom of each bounce, it's an opposite kind of relationship. In terms of measuring energy in chemistry, we usually use terms like exothermic, which means that energy is coming out to the surroundings by whatever process we're doing, and normally it comes out in the form of heat. Endothermic, on the other hand, is the energy change is absorbed by a system from the surroundings, and again, it's usually in the form of heat. So the image in the bottom right-hand corner is of an exothermic reaction. We know that heat's coming out of this whole thing. Your laws, the laws of conservation of mass, of energy, and of matter and energy. In terms of these laws, they are laws in chemistry, so that means that, yeah, they're always true. There aren't points in time when these are not true. We can convert between the two when it comes to binding energy, and we'll talk about that in terms of chemistry. That's something that was figured out in physics and applied to chemistry. The law of conservation of mass, on one hand, is that there's no observable change in the quantity of matter during a chemical reaction. So that's what this is showing you. The two solutions are separate on the balance, weighing 300.23 grams, and when they're mixed, the chemical reaction's complete. They still have the same final mass. Now, the law of conservation of energy says you can't create or destroy that. It can only be converted between different forms. And since chemistry is a study of change, this becomes very important during this study. The law of matter and energy is that the combined amount of these two in the entire universe, matter and energy, is fixed, and therefore we can never go ahead and change that. The different states of matter that we'll talk about in in chemistry, solids, they have a fixed, definite shape. They don't occupy the entire volume of their container, and the atoms or molecules are very close together in this state. Liquid, on the other hand, a lot of more empty space than in a solid. The molecules are free kind of to move around each other. They have a definite volume, but they occupy the shape of the container. Gases, on the other hand, mostly empty space, so the atoms and molecules are free to move around inside the container, so they occupy both the container's volume and shape. There's two other states of matter that come up. We don't really deal with them very much in first-time chemistry, but it's kind of fun to talk about them. The first is a plasma, and we'll talk about this when we return a little bit from school if there's questions on it and that kind of stuff. But here's an image of one of those hurricane balls, or however you want to say it, where you have the electricity inside, and when you touch it, it seems to complete a circuit with your hands, although you don't get a shock. And that's a form of a plasma in there, and we'll talk a little bit about that. A Bose-Einstein condensate, this is what happens at very low temperatures. The atoms seem to group together to share energy, and they seem to condense at temperatures near absolute zero on the Kelvin scale. Predicted property discovered through the study of physics, and with the help of the electron microscope we can actually see that this is what's occurring when it was predicted a long time ago. Chemical and physical properties, just so we know the difference there. Chemical properties, you can observe those by changes only in composition. You have to actually change the material in order to measure a chemical property. Things like combustibility or reactivity, those kind of things are definitely chemical properties, and when you measure those you end up with a totally different compound than where you started. Now physical properties, on the other hand, you can measure those without changing the substance. Things like density, color, odor, that kind of stuff, and even magnetism, which is the image there on the bottom of the screen. That kind of stuff you can measure without changing the substance. For example, if you have a piece of paper and you tear up the piece of paper, that's a physical property. You still have pieces of paper. Now if you burn the piece of paper, you no longer have paper, you now have ash. That is a chemical property of the paper. So that's a little bit about those. In terms of mixtures, we've talked about these a lot, just so you know what's going on there. A mixture is defined as a combination of two or more pure substances. You can have heterogeneous mixtures which are not uniform, so throughout the mixture they're different in composition as you go through that. Homogeneous mixtures are uniform throughout, so the milk is a heterogeneous mixture as you let it settle, and the salt water is homogeneous, meaning it's going to be the same throughout. And we'll talk about how to tell those two apart a little bit later in the year, but just for right now you need to know those two differences. Solutions are a form of a homogeneous mixture. They cannot they're uniform throughout as you look at those. A substance is something that cannot be broken down by physical means. You have to go through chemical means to break that apart. A compound is a substance that can be decomposed by chemical means, always found in the same ratio by mass, so the atoms combine in fixed ratios, like water being 2 hydrogen atoms and an oxygen atom. That's a form of a chemical compound. Then there's elements, and this can't be decomposed into simpler substances by chemical changes. If you want to break down an element, you have to go into something other than chemical changes, and we'll talk about that when we get to it in the year. But just so you know the difference between a substance, a compound, and an element. Make sure that you look at those in chapter 1 of your reading. In terms of the metric system, which is usually abbreviated as SI in your book, you'll go ahead and you'll see all different kinds of prefixes and things like that for the metric system. Most of you are familiar with prefixes like kilo in the kilometer, or centi in the centimeter, or milli in the millimeter. But we use everything in chemistry from mega, which means a million, all the way down to pico. So very wide range of metric system prefixes that you need to be familiar with. Now, the abbreviations and stuff, you can find those in your textbook in the appendixes in the back. Appendix C, it's on page A8 in the back, and they're also found on the back cover of the book. Now, in terms of measurements, we measure different things in chemistry. We can measure mass and length and volume. Mass is the amount of matter, and it doesn't vary by position. So no matter where you take the material, it'll have the same mass, as opposed to weight, which a lot of times in chemistry, those two terms are used interchangeably, and they can be very confusing. Weight is a gravitational attraction, and it varies by position. The base unit for mass is the kilogram in the metric system. Length is a measurement of distance. The base unit is the meter. Volume is space occupied, and you can see some different volume measurements on this picture. We use the liter or the milliliter, and just so you're familiar with this, 1 milliliter in the metric system is the equivalent of 1 cubic centimeter. In terms of significant figures, when we look at this kind of stuff, we talk about such things as accuracy and precision. These deal with measurements. Significant figures are only for measured numbers, and they cause a pretty big headache for first-year chemistry students. But by the time you're in AP chemistry, you're actually, well, maybe not so much, but you're actually very familiar with sig figs, and we'll work on them throughout the year. Now, accuracy and precision are two terms that are used when you're talking about measurements. Accuracy deals with how close a measured number is to the correct value, to the value published in a chart or what's known to be correct, and precision is how close individual measurements are to each other. So if you look at the two bullseyes, the top bullseye is neither accurate nor is it precise. The four marks on the bullseye are all at different areas of the bullseye. So if you're looking at that, I might say you have moderate accuracy, but you're not very precise. Now, the bottom bullseye has very high precision, but the accuracy is a little off. So typically, if you're talking about shooting at a bullseye, that would be a problem with the instrument you're using to hit the bullseye. So that's where that comes from. Now, as we talk about sig figs, just remember that these are numbers in measurements and numbers in calculations as we go through and do this. Now, sig figs themselves can be very difficult to understand, so we'll talk about these when we return. We'll work some problems, and there'll probably even be a later podcast on how to do sig figs with multiplication and division, addition and subtraction, how to look at sig figs, and how to go through and do that. But this isn't really the time for that. You can get that from the reading if you need to. Chapter 1 also includes a little coverage on ratios. They talk about percentages, density, and specific gravity. Just so you know that, density is a ratio of mass to volume. So you take the mass of a substance, divide by the volume that it occupies, and you'll get the density. And that is a physical property, meaning it will never change. It will always be the same given the temperature. Specific gravity is a ratio of the density to the density of water, both at the same temperature. Since it is a ratio in that respect of density to density, it has no units on its answer. So we can use that as calculations too, if we know the specific gravity of a substance. So those are different ratios that show up. Percentages, most of you are pretty good with figuring percentage, and again, we'll cover that as we get to it in class. Again, if there's questions on the homework problems that come up, we'll cover those when we return to school in August. Energy is one of the last topics that's talked about in this first chapter, which is just the foundations, the underlying information that you need to know from here on out in all the chapters of this book. As you go through and you do your readings or listen to these or take notes in class or work on problems, this stuff comes up over and over. So if you miss any of this stuff, it's very important that we get it taken care of early on. The term energy is the ability, the capacity to do work. And the first type that we have is we talk about temperature, which is a measure of the intensity of heat. It's defined as the average kinetic energy of a substance in terms of motion of the molecules. Heat is thermal energy. It always flows from a hot body to a cold body. So we've got that going on there. Temperature, just so you know, in chemistry we typically use the Celsius or the Kelvin scale in order to convert those two. You take your degrees Celsius and you add 273 to it to get to kelvins. Kelvin is an absolute scale. It stops at 0, so 0 Kelvin means there is absolutely no molecular motion. And go from there. We don't use Fahrenheit very much, but we'll talk about that conversion in case you need the help with it. Joules, with the symbol capital letter J, that's the metric system unit of energy and work, and it's typically explained as it's 1 kilogram meter squared per second squared. So it's a mass moving at a certain speed. Calorie, on the other hand, is it's the energy needed to change 1 gram of water by 1 degree Celsius. Its definition then in metric system is 4.184 joules is the amount of energy in a calorie. And that's specific to converting between the two units of energy measurements. Specific heat is the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. The units are joules per gram degree Celsius. And we can actually calculate heat by taking the specific heat of something, and we can look that up in a handbook of chemistry or physics. We'll work on that when we return, and multiplying by the mass and the change in temperature. And that'll actually give you the heat calculation. Heat capacity is the only difference between specific heat and heat capacity is heat capacity does not include mass in the units. It's just joules per gram degree Celsius. So it's the amount of heat needed to turn a body 1 degree Celsius. So some of the things that you should have learned about here when you're done with chapter 1 and the homework that's in it. Again, just to review those things, it's the difference between endo and exothermic and so on. You can read down this list. We covered it at the beginning, and then up next we'll talk about chapter 2 a little bit. That's the next screencast, so you can go through. Again, these are the things from chapter 1 that are most important for you to know about at the end of your study of chapter 1.